Okay, guys, let's go back to chapter 11. This is section 2, and we're talking about electrolytes. And what are electrolytes? Well, there's in a solution, typically water, we need something to be able to move through the solvent, and it needs to be charged to be an electrolyte. So, substances that dissolve in water and undergo a physical or chemical change to produce ions. Non-electrolytes are things that, when dissolved in water, do not produce ions. And that kind of makes sense. We can break it down into two categories for electrolytes. We can have a strong electrolyte, which means that basically all of it breaks into ions. And we can have weak electrolytes, where only a small amount of it is broken into ions. And so an example of a strong electrolyte would be something like hydrochloric acid or sodium chloride that has a pretty high solubility. Something that would be a weak electrolyte would be something like acetic acid, which we find in vinegar, and it only dissolves or ionizes about 5%. So here we have a picture, and we could do this in class. I can get out the probeware and you can see conductance, and that might be a good demo to do. If we have a non-electrolyte, that would be something like sugar. It will dissolve in water, but it will not have the ability to carry current through the solution, so the light bulb wouldn't glow. If we have something like a strong electrolyte, like maybe hydrochloric acid, which is basically stomach acid, if it were dissolved in water, it would be a strong electrolyte, and we'd get a very bright light, and that would glow very well. And then if we put acetic acid in, we would see a little bit of glow, but not very much, because it doesn't ionize very much, means it doesn't have a lot of particles to move through the solution to carry charge. So, ionic electrolytes, water and other polar molecules are attracted to ions. And so the electrostatic interaction between the ion and the solvent, in this case, the molecule of water, it would interact with a dipole on the water molecule. And so there is a dipole on water where the oxygen would be more negative because it has more electronegativity than the hydrogen. And so the negative ions would be attracted to the hydrogen area of the molecule, and the anions or the cations would be attracted to the negative or oxygen end of the molecule. And so water molecules then surround and what we call solvate, cover and solvent, the separated ions. And this process is known as dissociation. So here we have a diagram. We see the hydrogens are white, the oxygens are red, and the chlorines are green, and potassiums are purple. And so the white hydrogen end of the water molecule is attracted to the negative chloride ion, and the red end of water is the oxygen, which is attracted to the cation or potassium. And so those interactions help to break the interactions between the potassium chloride ionic compound. So there are some competing forces. And so the ion-ion interaction, if this is the dominant force, then the compound will be pulled into the solution and it will have a very high water solubility. If the force of the attraction between the oppositely charged ions, if this is the dominant force, then the compound tends to remain undissolved. So if the interaction between the ions is really great, it'll tend to have low solubility. If the attraction to water is very high, then it'll have higher solubility. Some covalent compounds are electrolytes because they chemically react with water to produce ions. HCl is an example. So, and it dissolves completely or dissociates completely in water. So that's the end of 12.2, and we will come back for 12.3. See you later.